This week, we are going to focus on the matrix calculations that's behind self-attention. So just to recap what we have learned last week. So this is how we define self-attention. So attention QKV, so query key value equals to softmap KQ transpose divided by d of k, which is the dimension of the key vector, into the multiplied with the value vector. So just to go over this again a little bit. So what are attention? How transformer establish relations among word with attention. So over here, Tom eats pizza, pizza eats Tom, right? So it has two different meanings. So this is how it depends on where the word is positioned, and that changes the meaning. So if I take an example of this architecture, so pizza is awesome, great, EOS. So end of sequence, right? So this is word embedding. So each and every word can be represented or encoded in terms of a vector. So this vector can be a one value, a two-dimensional vector, could be a 256, 100, 1048, and so on. So it depends on the language model or the model that you are trying to build. So each and every word is represented with a vector space or with the word embedding, and then they are summed up with a positional encoding. So where is the position? So pizza is at position 1, is at 2, and likewise, right? So just again another example, the pizza came out of the oven and it tasted good. So transformers have attentions to correct which word it should be associated with. Is it oven or is it pizza? Okay, so let's go over just a recap of how query, key, and value work. So let's say that there is a last name versus number, and you have a bunch of last names, and whoever has that last name should go to that room. Okay. So I have a name, last name as Sumit, and then there is another last name that comes very close to that last to Sumit, right? So this is my query. So I am trying to figure out from my database which is the query which is closest to this name, and I figured out it's Sumit, and then this is the key according to which I'm getting a value. So when I'm getting this key, it's returning 202, and it's telling me that you should put this or put this person in room number 202. Okay, so let's just look at this. So that's the kind of the concept that you can have from a database. Now, moving back to or going back to the word embedding and positional embedding. So right now, we are only concerned with a two-dimensional word embedding or word encoded. So pizza is encoded as like a two with a vector of value or element size 2, and then it is added with a position vector, so 1 0 0 0 for example, and then that's giving me a value after addition as 0.1 2.13. So these are just fake values that I've put for just notation purposes. Okay, so then I move on to is, and then I can move on to awesome, and then it has its corresponding positional values as well as the word embedding. So finally, we are creating a word encoded vectors or word encoded matrix. So which is corresponding to pizza is awesome end of sequence. So this is my pizza represented with 0.1 and 2.13. 0.11, 2.13, and so on and so forth. Okay. Okay. So now, so we are taking that value of the encoded word embedding. So because we started with two encoded value with multipliers with 2D weight matrix. So if we had started with 512 encoded value, we would have 512 cross 512 weight matrix. So this is what we started with, and then our weight matrix for the query. This is the weight matrix for query, and then we multiply and we again get 2 by 2 query matrix value, right? So in a similar way, we can calculate this for key, and we can also calculate this for value. Okay, so value width. So remember, this is a transpose. So it's the way how Pytorch will interpret it, or any coding language will interpret it. So it's better to always put as Q, K, and transpose, or multiply this with transpose. When we will be writing the code in Pytorch, it will make more sense. So just wait until that. Okay. So the next thing is just a matrix kind of representation. So QKT will give us a non-scaled value. Okay, and then we will scale this with delta dk, which is the dimension of k, or square root of dk, which is the square root of the dimension of k. Okay. Okay. So what happens now is if we go back to the equation again. So now we have qk and p. Now we will apply a softmax. So this is my scaled similarity score, and then we are applying a softmax over it. So what will happen when we add a softmax over it? So softmax multiplied with the similarity vector, scale similarity vector, will give me another matrix, and all the row values of this will actually figure or actually sum up to 1. Okay, so all these values taken together will actually sum up to 1. Then I'm going to multiply it with p. Okay, so what does that mean? So pizza is, so if I can break it down over here a little bit more. So pizza is awesome and pizza is awesome. Okay, so let's take this as a 3 by 3 matrix. So what these values represent is pizza when it is represented with pizza, or when we are trying to find a similarity score of pizza with pizza, it's 0.38. Okay, and which so that means it's of course 38% similar to pizza, 4% similar to is. So see, it can have a greater value even if the word is different, right? And then 0.9% similar to awesome. Okay, so it has a more probably a more similarity score to awesome. Okay, so pizza is awesome. Then we have 0.38, 0.4. So now we get this matrix, and then we are calculating the value matrix. So we multiply this with value matrix, and let's say after you calculate the first row and the first column, you will have a total value of 1.0. In other words, the percentages that comes out of the softmax tells us how much influence each word should have on the final encoding for a given word. So, so pizza is actually, so when I am thinking of pizza, let's just draw this a little bit. So pizza is basically 0.38. So this is the value of value matrix, let's say 0.6. Uh, so pizza depends upon pizza. So this is what we get from pizza, right? Then we have 0.4. into, let's say, whatever comes for the value matrix. Okay, and this one is yield. Okay, and 0.24 into 2.86. So, and this is coming from awesome. So this one is a similarity score that I have with awesome. Okay. Okay. So in other words, the percentage that comes out of softmax. So this percentage tells us how much influence each word should have on the final encoding of the given word. So the final encoding of the given word is actually having all these effects, right? So these are all the percentage effects of the other words that is having on pizza. Okay. So, so 38% of the first value of pizza, 40% of the first value is, and 24% of the first value for awesome. Yeah. Okay, so now we calculate this QT with value, and then we have a self-attention score. So now we get our self-attention score. So pizza is awesome. Finally, our attention value for pizza is awesome is now calculated, and this is the self-attention score. Okay, so now how do we actually write this in terms of our Pytorch module? So let's define the class self-attention. So class self-attention inherits nn.module. So nn.module is basically a class in Pytorch which has all the methods and functionalities for a neural network. And we need to inherit this inside our self-attention class, right? Now we start with the definition init, and then we have d model equals to 2 row dimension, column dimension. So the row dimension is basically how many encoded value you want to use for your word embedding. So for this example, we are using 2. It can be 256, 512, etc., etc. Okay. And then you have a row dimension and a column dimension. So this we are going to use for later purpose. So maybe for a batch, if we want to use a batch. So we can use one of these dummy values or one of these variables to use it for a batch later on. Okay, and then so these are convenience parameter to easily modify row and column index of the data. This could be batches of data. Okay. Now we need to inherit the parent class because we are inheriting the class init module. So how do you inherit that? Super dot underscore init. So this is from which comes from the parent class, right? Okay. Now let's try to write the weight matrix of the query vector. So we pass W underscore Q equals to NN linear. So in features equals to D for G module, out features G modules, and we can keep the bias false. Okay, so just like a default value. So NN linear creates the weight matrix. So this is now creating the weight matrix, and we which will help us in calculating. So once we get the word embedding or the de-embedding. So word embedding, if once we pass it, we multiply with W underscore Q to get our query matrix. Okay, so similarly, we can use this for query, we can use this for, yeah, we can use this for key, we can use this for value, like it follows the same rule, right? So in feature number of rows and out feature number of columns, and that will create the key. We can calculate the value. So this is the key. Similar expression W underscore V is a similar expression over here. And that gives me the value matrix. And then finally, let's put everything together. Self dot W underscore Q equals to NN linear. And then with a D model, out feature, in featured equals to. So because we want to get it again a 2 by 2 or whatever the dimension is, as I mentioned, right? So yeah, so we can just use it the same way. In feature D model, out feature D model. And then finally, we are going to hold the values of row underscore dimension and column underscore dimension in a variable. Okay, so now, so this is putting it everything together. Now let's write the forward method. The forward method takes the token embeddings, right? So this is your token embedding. So forward method takes your token embedding. And then we define Q equals to self dot W underscore Q, and it takes the token embedding. So that will make that will create a matrix multiplication between the weight matrix of the query, and it returns the query matrix, right? So we can have this for all the calculating all Q, K, and P. And then we are calculating the similarity matrix, which is a Torch multiplication, KQ transpose. Dimension equals to dimension 0 is self dot row dimension, and dimension 1 self dot column dimension. Okay, and then we have to now check the self dot column dimension. Okay, because we kept that column dimension as a variable value, right? So k dot size with the column dimension. So that basically this is the square root of det and dk. Torch tensor, so that you have to convert it to a tensor. And finally, we get a scaled, so that gives us a scaled similarity score. And now we calculate the attention percentage with using a softmax, right? Where we can calculate how much each word is contributing to another word, right? So this is the softmax part of it. And then applying the softmax part to calculate, to scale similarities determines the percentage of influence each token should have on the other. And then finally, we calculate the attention scores by using the Torch multiplication of attention percentage with the value. Okay. So going ahead here, just run this. So this is all the import modules that we need for this work. Torch.nn as nn, torch as nn.function, so which gives you softmax actually. Then we code the self-attention, so similar what I mentioned. And so we calculate the self-dot, so weight of Q, weight query, weight of key, weight of value, right? And just using the NN linear. Then you write the forward method, which takes in the token encoding, right? Calculate the similarity score, scale similarity score, and then the softmax percent, and it returns the associated percent, and then add them up all, right? So with the value matrix, you add it up and return the scores. So it's so in other way, we can also kind of give a matrix encoding. So here we can give a matrix encoding and then call the self-attention module to work on our encoding data and give us an attention score back, the attention scores back. Or you can actually, so I will leave this to you to just check this out one by one, how the same value comes at the, so you calculate each step and then you receive the same value at the end. So just going over step by step, it kind of gives you back the same value. Okay. So next class, we will use this attention module and self-attention module, and we will solve a problem, a training problem. So this is not a training problem. So next class, we will work on a training problem. Okay. So then we will move on to uh, to the to the algorithmic part. So today we'll also discuss about the hash maps, and we'll solve a problem of analysis. These are kind of the easier or the easy algorithmic questions that you get asked in interview. So we'll discuss about that now. Problem statement, and we'll try to solve this in two ways. So one is hash map, the other one is sorting. Though I prefer this technique, the better one is hash map. So given two strings S and T, return true if T is an anagram of S and false otherwise. So S anagram and T is it's just a version of the S, right? So it's a jumbled up version of S, right? As you can see. So if these two have the same number, so first criteria is it should have the same length, and then it should have the same characters in the string, right? So moving on with the assumption of hash map, let me so here so if we are trying to use hash map, then the space, so the space complexity, it's becoming O of n, right? And we looked at earlier problems, the time complexity still is, I'm sorry, O of n, right? So this is my time complexity. So how can we go about by using hash maps? So basically we have to use two hash maps for S and T. Okay. So for S, we have a hash map, and we are checking how many times. So this is my character, right? And count. Okay. So count number of times, or n. Maybe I can put this as n. So and then we can do the same for. So if the lengths are same, then we do this character, right? And then n, which is the count. So for this, A appears 3 times, right? And then your A in T also appears 3 times, and followed by N, G, which are appearing once, right? M, okay, once. So then we fill both the S and T hash maps, and then we start comparing. We will start comparing S and T. Okay. So if A is appearing 3 times, A is there in T and it appears 3 times, N is appear in N, S and T and appears 1 time. And then we just keep comparing. And if this comparison is returns, if the comparison works, then we will return true, right? And if it fails, then it will return false. So there is another way to go about doing this. So that will be through sorting. So we will first sort all the AA then G M N R. So this is the sorting we will do for S, and then we'll do a sorting for T, right? A G M N R, and then we can simply compare this two, right? So if we start comparing two sorted lists, and then we will end up with we will not end up with extra space, but my time complexity will still remain of n, and but I don't end up with some extra space over here, right? Like the hash map. But you might ask me that what about the sorting? So n log n, right? That. So what about that? Okay. So it depends on how you want to solve this. So if we consider the sort time complexity, then we will end up with then we will end up in a different domain, but time complexity domain. But otherwise, this can also be one of the solutions. However, I'll just go over this solution using a hash map. Okay. So let's go over this and start coding. So then first class, let's do solution, and then def is anagram. So we have S is a string, T is a string, and then we are going to uh, return a boolean. Right? So if first we are checking if length of f is uh, not equal to length of t, then we return false. Right? But if the length is same, then we will initialize two hash maps. Right? Hash maps. Let's call it as count s and count t. Yeah. So then we start filling out this hash map. So count s and s of I, right? So that's the character wise is 1 plus or count. So we'll do count s dot get. So this means that we are trying to get the number of times that particular character appears. So, yeah, and then let's put similar for let's do this for count t, and it should be for t, and then just do t. We'll replace this with t. And so you are getting if it's already there, otherwise 0. And then now we will do the comparison for c in count s. Yeah, actually. So if count sc not equal to count dot get c comma 0, then return false, otherwise will return true. Right? and then solve equals to solution. Okay, and anagram. Okay, fine. Yeah, and then let's remove the a, and it's going to return false. Okay, so that's the solution, and thanks for watching.